Today we'll be quickly covering the gamma function and the Feynman technique of deriving under the integral sign. So the gamma function just extends the factorial function over the reals and is given by the integral of x to the power of z minus 1 times e to the negative x dx from 0 to the infinity. So, this guy right here. And yeah, this is really a very useful result, as now you can do like pi factorial, right? A half factorial, or, any weird factorial you want. Now, if you haven't seen my video on the gamma distribution, you should probably check that out after you finish this video. But for now, keep in mind that the gamma function is essentially the normalization constant for the gamma distribution. And that's why its CDF, right, equals 1 at the end. This fact here, that gamma z plus 1 equals z gamma z, is super useful in simplifying integrals that use the gamma function. And as you might have guessed, right, can be used with induction to prove that gamma just extends factorial. So let's just jump right into it here. You'll notice that gamma z plus 1 equals this guy, just because gamma z equals that. And we can use integration by parts to simplify this, right? If all we do is let u equal t to the power of z, and then we have dv equals e to the power of negative t times dt, which implies, this du equals this guy here, and our v equals that. And then here, right, I'm just applying our integration by parts. This is the standard formula, Then we get our left side, this guy. You'll notice that it actually equals 0. Because as t goes to infinity, right, our e to the negative t goes to 0. And where t is 0, our e to the negative t is 1, and t is 0, so, we get 0. And now you'll see that our right integral, right, is just gamma z. When we take our constant z out, and we're done. Now, before I show you our final property of the gamma function, right, think about this note at the bottom and what this might imply about the gamma function. Think factorial. So Feynman's trick is just to derive under the integral sign. And to show you how that works, we're just going to look at the main result of the gamma function. This guy right here. And you'll recall from calculus that this integral equals 1 and this one equals 1 over t. You can verify this guy just by doing by parts. And you should do that if you don't remember this result by heart. Now, here, if we differentiate with respect to t, we get this guy. And if we do that n times, eventually you'll notice that this is the pattern. And the reason we have this pattern, right, it's pretty straightforward. Each time we take down this negative, that's where this comes from. And each time we take down an x, right? So that's where these x to the power of n is. And on our right-hand side, this negative 1 to the power of n comes from the fact that this is, under the fraction. So it's negative, right? And our exponent is negative, I should say. And we have n plus 1 at the bottom instead of n, right? Because when we started, we had t to the power of 1, not t to the power of 0. This guy right here. And more interestingly, right, this n factorial comes from bringing this guy down each time, right? Each time you're multiplying the previous result by that one, just like n factorial. So once we cancel these guys out, right, we get this result. And then once we set t equal to 1, you'll see that the left-hand side is our gamma z plus 1, and this is our z factorial and n factorial. So before I show you some practice problems, I wrote, pause the video here, think about this note, and take as long as you need to make sure you understand this slide. Work out a couple iterations yourself, maybe up to 3, whatever. You'll see that this quickly emerges. So these are just some practice problems of varying difficulty, and I encourage you to give these a shot. Either way, thanks for listening. Feel free to ask your questions in the comments below, and please do let me know if I made any mistakes at any point in this video. And yeah, I'll see you guys next time.